Okay, so we now come to the next part of the program where we have our lightning talks. And each of these is a 3-minute pre-recorded presentation, and we have 10 projects on different topics related to computable biomedical knowledge. So the abstracts for all of these talks and the others which have been accepted for publication are available in the email that was sent you that had the subject line MCBK meeting, login instructions and meeting tips. And also you can just go straight to the MCBK website to find those links. So after the talks, you need to choose the Zoom meetings which are specific to the talk that you would like to go to ask the speakers questions. And you're free to move in and out of the Zoom meetings, and we encourage this. So after we've heard from the lightning talks, we'll be introducing the Zoom breakout discussions, and I'll have a bit more information then about some additional speakers who'll be present in the lightning talk sessions. So we encourage you now to go ahead and listen to the lightning talks.
Everyone, my name is Jen Du from Peking University. The title of this talk here is a PICO-based knowledge graph for representing clinical evidence reported in clinicaltrials.gov. Compared with bibliometric databases such as PubMed, clinical trial registries contain rich information, especially negative results. We constructed a graph using this data to help evidence synthesis in a more systematic manner. ClinicalTrials.gov provides two data formats. One is a CSV format, which does not require programming skills and displays basic trial information. Unfortunately, it has several limitations, such as lack of statistical results, especially the effects of interventions on outcomes. The other is SML format, which presents detailed information such as PICO elements, statistical measures, and adverse events. The pipeline for extracting evidence in clinicaltrials.gov is presented on this slide. After collecting all trial data, we normalized medical entities to UMRS and all the CDM vocabularies. We then define relations between intervention and outcome by p-value or confidence interval. We define that its p-value less than 0.05 and both the lower and upper CI value smaller than 1 or greater than 1. Then it relates to have significant difference. Ultimately, we find 232,000 statistical results. Among them, 36% are positive results, while 64% are negative results. We then loaded the content into a graph database to make PICO elements and the effect easy to query. A simplified schema for a clinical trial is presented on the slide. Unlike scientific publications, which tend to omit or even not publish trials with negative results, this data include all positive and negative results, as well as adverse events. So the knowledge graph is expected to give a whole picture of reported results of clinical trials and provide a computable format for evidence synthesis. That's all. Thank you.
Hello, my name is Josh Richardson, and on behalf of my co-authors and members of the MCBK Trust and Policy Work Group, I'm presenting results from a recent publication in Learning Health Systems Journal on a survey of computable biomedical knowledge repositories, developing a desiderata for conveying trust. With this work, we assessed governance practices for trust among a convenient sample of CBK repositories in the United States. For the CBK ecosystem to develop and make knowledge fair, findable, accessible, interoperable, and reusable, trust is a necessary condition. Without trust, the collective endeavor of building and sharing CBK will not succeed. We therefore conducted a survey of a convenient sample of CBK repositories to understand how they may instantiate trust within their policies, procedures, and tools. We primarily organized the online survey questions by Lin et al.'s Trust Principles for Digital Repositories: Transparency, Responsibility, User Focus, Sustainability, and Technology. We organized the findings into categories of common to uncommon principles, such as that repositories commonly conveyed transparency through the publication of date metadata, or for the responsibility principle, 8 of 13 repositories stored CBK in machine-readable formats, thereby increasing the integrity of their knowledge holdings. Less commonly, organizations attributed metadata with user history or feedback, and few reportedly included patients in their governance decision-making. Our findings identified common principles and practices among CBK repositories, especially around metadata, to capture aspects of the knowledge itself, but less so for addressing issues around gaining user feedback, or importantly, involving patients in the governance of CBK. With that, we published a proposed set of desiderata for CBK repositories, which seeks to reinforce some common practices and address gaps in others. Our work is available online via open access and learning health systems. Thank you, and I look forward to answering your questions at the conference Q&A.
Good morning and good evening, everyone. It's a great honor to have the opportunity to present my research at the MCBK Global Meeting 2022. I'm Guilan Kong from the National Institute of Health Data Science at Peking University. Today, I'll introduce an innovative evidential reasoning-based and knowledge and data-driven modeling methodology for clinical decision support. Traditionally, clinical decision support systems, CDSS, can be classified as knowledge-driven and data-driven systems. Conventional knowledge-driven CDSS are easy to understand, but knowledge-based construction is a challenging job, especially for uncertainty, representation, and inference. With the accumulation of big data in medicine, data-driven CDSS have attracted researchers' attentions. However, most data-driven CDSS are black box, and low-quality data may produce inaccurate CDSS. In such a situation, knowledge and data-driven CDSS have been recommended in recent decades. In this study, I propose an evidential reasoning-based knowledge and data-driven ERKD modeling methodology. The ERKD model consists of 3 submodels: a data-driven model, a knowledge-driven model, and a knowledge and data-driven fusion model for integrating the results generated by knowledge-driven and data-driven models. And in the knowledge-driven model, domain knowledge is represented using belief degrees and new parameters, including rule weight, attribute matching degree, and belief degrees in consequence are introduced. And the inference mechanism is implemented using the evidential reasoning approach, which can produce a result with combined belief degree distributed on possible consequence. And in the data-driven model, real-world evidence is mined from real-world data using a generalized Bayesian method, and the evidence is profiled using a distribution format with evidence weight, evidence reliability, independence index among evidence, and a degree of belief in each medical outcome. And the evidential reasoning rule is used to do evidence combination. And in the ERKD model, domain knowledge and real-world data can be used complementary. The data-driven model is not a black box here. The real-world evidence and the evidence combination process are explainable. Moreover, uncertainties can be well represented and inferred in the model. Next step, we'll use the ERKD model in practice for CKD management. That's all about ERKD. Thank you very much for your attention.
Hi, my name is Joanne Dane-Bostel, and I'll be showing tools on the Fever platform to convert Medline and clinicaltrials.gov data to FHIR. Technical standards such as Health Level 7 Fast Healthcare Interoperability Resources, or FHIR, advanced mobilization of computable biomedical knowledge with packets of information called resources. We have extended FIRE to evidence-based medicine by creating resources to represent scientific knowledge artifacts. We now have citation, evidence, evidence variable, evidence report, research study, and artifact assessment FIRE resources to help us represent scientific knowledge. Consider 7 different systems managing data about scientific studies. Each has their own format. If we want to exchange data from one system to another, we would need 42 data exchange tools to do so. Using a hub and spoke model, if we use a standard form for data exchange like HL7 FIRE, we could arrive at the same objective of interoperable data exchange with only 14 tools. In fact, we've begun the process by creating tools on the Fever platform to convert data from Medline and to and from clinicaltrials.gov to FIRE. We've also created a tool that converts RIS to FIRE, which will help with exchange of data from citation managers like Zotero and other RIS-based systems like Pico Portal. Here you can see the Medline converter tool on the Fever platform. Simply enter any PubMed ID number, and voila, a FIRE citation resource in JSON format has been created on the Fever platform. Simply change tabs and you can view this resource in human readable form without any knowledge of JSON. The converter tool also creates a citation summary that can be used in a reference list. The Fever platform also has a clinicaltrials.gov converter, which converts data from the protocol and results sections of a study record on clinicaltrials.gov to resources in FIRE JSON format. Entering the clinicaltrials.gov NCT number for a research study will result in the creation of many FIRE resources, including a research study resource and a number of other linked resources structured to handle other types of data, such as citation for the related article, evidence variable for outcome measures, and evidence resources for statistics. In this screenshot, you can see a link for the eligibility criteria. When you click this link, you are now in the evidence variable viewer, seeing a human readable view of the evidence variable resource. This view shows the human readable form. Some clinicaltrials.gov studies are extensive and will result in the creation of over 1,000 FIRE resources. The Fever platform supports the COVID-19 Knowledge Accelerator Initiative, or COCA, an open virtual group that works to inform and develop standards, terminologies, and tools for the computable expression of scientific evidence and guidance. You can participate in 12 open virtual weekly meetings shown here. Details can be found at the link shown on the slide at tinyurl.com/COCA2021. Thank you.
The Fast Evidence Interoperability Resources, or Fever platform, is freely available to support creation and viewing of structured data for scientific knowledge. The Fever platform uses the FIRE standard for structuring the data. HL7's FIRE is widely adopted for health data exchange. With an HL7 project called EBM on FIRE, we are extending FIRE for exchange of scientific data, including knowledge artifact structures for citation, for evidence variable, for evidence report, for research study, and artifact assessment to express comments, ratings, or classifiers of other knowledge artifacts. Knowledge artifacts are called resources. You can view resources on fever.net without logging in. You can view any resource in the JSON view, which shows you the actual JSON. In this example, we're viewing JSON for a single evidence variable resource. All resource viewers on the Fever platform have a text view, and you can see the same JSON in outline form, making it easier to view and interpret. Some specialized resource viewers, like the evidence variable viewer shown here, have user-friendly displays tailored to the context of use. In this example, we are displaying a complex set of inclusion criteria for a research study. You can add resources to fever.net. There is no cost, but you do have to log in because you're the only one with edit rights to update the resources you add. You can submit any valid JSON for a resource instance, and you can submit an array of up to 10 resources at a time. We also have specialized builder tools to help you create resources without any need to directly interact with or understand the JSON itself. Here is an example with Citation Builder. You can see easy-to-use data entry forms for identifiers, related identifiers, and titles on the screen. And in the navigation menu, you can see many other components like classifiers and the author list under contributors that you can edit, each with custom user-friendly data entry forms. The Fever platform is developing to support other systems and platforms using FHIR for electronic data exchange. And we have a converter tool. You can put in a PubMed ID and convert a Medline record to a citation resource, put in an NCT identifier, convert clinicaltrials.gov study record to hundreds of resources, put in an array of resources in RIS form and get the JSON output. You can collaborate with us. We are collaborating with a global group to create the scientific evidence code system and have a My Ballot tool to help facilitate voting across hundreds of terms. We collaborated with COVID Knowledge Accelerator to show how to look at recommendations across guidelines for COVID. And you can follow the tiny URL here to learn about COVID Knowledge Accelerator and see the weekly meeting schedule, 12 active open working group meetings. Thank you.
Hello, today I'll be talking about designing interprofessional education to foster learning health systems. We need a critical mass of people with the skills to build a learning healthcare system if we are going to reap the benefits of the digital transformation of healthcare. When we asked numerous healthcare leaders what the biggest barriers to implementing digital innovations were, overwhelmingly the answer that we received is that the current workforce was not adequately skilled to undertake the task. The Centre for Digital Transformation of Health is a new initiative by the University of Melbourne. Within our education and workforce strategic pillar, we are focused on building capacity and capability in digital health. The concept of the learning healthcare system is relatively new in Australia, and we have employed this concept to model the mindset of rapid and continuous cycles of quality improvement through interrogation of data, application of knowledge and insights gained into practice in real time. Thus far, we have developed two major educational programs of work. These include the Applied Learning Health System short course targeting interprofessionals working in healthcare and the year-long Fellowship Academy, focused on developing the leadership capabilities of emerging clinicians. The aim is to build skills to take on the role of a digital health champion within their organization. And the hope is that these individuals will continue to foster learning communities, mentor teams, and lead LSH projects in the future. The short course is modeled around the flipped classroom idea, where learners come to the class having undertaken their own self-guided learning. In-class workshops are focused on working through practical problems in the integrated case study, in teams, and allows learners to share experiences and apply learnings. In the Academy, fellows undertake a LSH project alongside an ongoing education curriculum. Over the course of the year, they are receiving support from mentors and expert panels. At the culmination of the year, they present their project at a symposium and submit their report and portfolio. We undertook evaluation of various elements of this programming, from capturing changes in self-confidence through pre and post surveys to measuring value, as well as undertaking follow-up interviews to dive deeper into applications of concepts and evolving digital health identity. So here's what we found. Post-course participant self-confidence in topics significantly increased in the short course participants and the fellows. The most valuable aspects of the course were rated as the instructors, guided workshops, pre-class activities, and collaborative learning. In terms of the learning health system framework, it helped participants organize their knowledge, gave them a language to converse with their professional peers, and gave them a toolkit to operate from. The fellows' biggest barrier to engagement was seeing themselves as a leader or champion. Interestingly, we observed a change in identity where pre-academy only 5 fellows saw themselves as needing to be a leader, and 3 months into the program, this changed to all 10 fellows seeing themselves as leaders. We present examples of LHS-specific education programs as a means of educating the health workforce to adopt LHS models into standard practice. However, it's evident that such a movement will require global and coordinated effort with significant training from the workforce to be able to undertake the utilize data to effectively improve practice. Moreover, organizations need to be prepared for this transformation with adequate infrastructure, effective change agents, and importantly, a growth mindset. Thank you.
Hello, everyone. This is Zhengyu Wu from the Advanced Institute of Information Technology, Peking University. And it's an honor for me to introduce our team's work on MCBK campaign today. And the theme is Integrate China, a platform for scaling CBK across practice. There is a contradiction between the growing needs for health services and the limited medical research all over the world, and scaling biomedical knowledge across clinical practice is critical to alleviating the contradiction. And the Agency for Healthcare Research and Quality in the United States has come up with the idea of learning health system, the core of which is the virtuous cycle of biomedical data, evidence, and clinical practice. In China, CBKs are dispersed and unexploited in a mass of healthcare systems, and the Category China platform is just a practice of learning health system in China, which has provided a platform for scaling CBK across practice more quickly, easily, and broadly. The Category China platform is developed based on the plugin architecture, and the basic framework consists of the knowledge libraries, knowledge active vectors, and an application platform. The workflow of the Category China is just as follows. First, the knowledge providers extract the actionable knowledge and make it machine ready. And second, the knowledge translators transform the CBKs as knowledge objects and archive them in the knowledge libraries. Then the knowledge active vectors are employed to activate, combine, and deploy the KOs as a comprehensive industry solution for a specific practice. And third, for the knowledge users who can apply health advice to real-world decisions, the platform provides them with a fully visual and interactive operating interface to apply the above industry solutions to different clinical scenarios. And at last, with the minimal communication cost, the latest CBKs could be translated into practice quickly and easily. As the first platform mobilizing CBK in China, the Category China focuses on the field of chronic diseases, and there have been 29 reusable knowledge objects for chronic diseases, 13 applications compatible with multiple clinical scenarios, and 2 special topics for the management of chronic kidney disease. In the future, Category China attempts to expand the clinical application scenarios and collect the real-world assessment data in clinical practice to guide the utilization and improvement. At last, I want to acknowledge the support of the knowledge grade team of University of Michigan Medical School, and we welcome more communications and collaborations on the Category platform. Thank you for your attention.
Hi, my name is Saj Azuli. This presentation is about knowledge sharing in the field of observational health studies. I'm going to present a solution, which is an application that we implemented in the context of the National COVID Cohort Collaborative Project within the National Institute of Health. So to give a little bit of context about the National Cohort COVID Collaborative Project within the NIH, also called N3C, it's a partnership between the NIH and a group of research hospitals. These research hospitals contributed data, which is electronic health records, to a national database hosted by the NIH in a secure data platform called the N3C Data Enclave. Researchers across universities in the US and abroad and pharmaceuticals can apply for access in this research platform and conduct research related to COVID-19 on electronic health records collected from the United States. So this just gives you an idea of the scale of the data platform: 14.5 million patients, 16 billion rows of electronic health records, 400 research projects created, data contributed by 80 hospitals and research centers. 2,600 researchers produced more than 80 publications in a variety of research topics all related to COVID-19. And so the challenge here was that the platform has strict governance rules. Teams of researchers work in separate workspaces across different data sensitivity tiers. So sharing of data and analysis across workspaces is not allowed for obvious governance rules. So what we implemented is the application called the Knowledge Store that enables secure sharing, making sharing low cost, and tracks provenance and reproducibility and attribution, and makes sharing of knowledge and artifacts discoverable and reduce duplicative work for researchers. And so this knowledge store allows the sharing of code logic, libraries, cohort definitions, models, and algorithms called knowledge objects securely while tracking provenance and attribution. And this, finally, to give you an idea of the impact of the knowledge store, there were 99 knowledge objects shared from various categories. The knowledge objects has been used more than 1,800 times by 127 research projects. And this contributed to the promotion of standardized logic and methods and helped accelerating research outputs from this national cohort COVID collaborative platform. Thank you for listening. This was all about the knowledge store in N3C.
I'm Howard Strasberg. Today I'm going to talk about mobilizing knowledge conclusions with CDS hooks. There are two methods for incorporating knowledge into clinical systems. In the first method, the local method, the knowledge artifacts and the knowledge execution engine both reside locally within the EHR. In the cloud method, the artifacts and the engine reside in the cloud. The EHR sends the patient data to the cloud service, which then returns knowledge conclusions back to the EHR. CDS hooks is an HL7 standard for trial use that provides a web service specification for the cloud method. The process begins with workflow triggers from the EHR, such as patient view, order select, and order sign, that trigger a call to the remote CDS hook service. The patient data are sent using FHIR. The service then evaluates the knowledge artifacts and the FHIR data with the execution engine and returns knowledge conclusions in the form of cards, which can contain information, suggested orders, or suggested Smart on FHIR apps. There are numerous advantages to the cloud method. The first has to do with content updates. In the local method, the content must be updated and kept current at each site. So there's a high risk of the content becoming out of sync with the latest evidence. Whereas in the cloud method, the content only needs to be updated in one location. Secondly, the effort required by the EHR or health IT system to implement the artifacts locally requires that each of these systems implement an engine that can evaluate the artifacts. So that's a significant burden on these systems. Whereas in the cloud method, these systems simply have to be able to call a cloud service, and that's all they need to do. When it comes to machine learning models, again, the cloud is a better fit because it can be impractical to replicate machine learning models in every local environment. Similarly, if you're talking about very large knowledge bases such as drug-drug interactions that could contain thousands of knowledge artifacts, again, it's impractical to deploy and keep current thousands of artifacts in every local environment, whereas the cloud service is a good fit for this purpose. Finally, we're all interested in a learning health system, and CDS Hooks actually has a feedback feature that keeps the cloud service informed of which suggestions were accepted. It's possible to do this in a local environment, but you'd have to collect local feedback from every site in different formats and normalize the data into a database, so it's harder to do. So we now come to our lightning question. Given that cloud-based CDS Hook services offer numerous advantages over local deployments for incorporating knowledge into clinical systems, should we focus more on mobilizing knowledge conclusions rather than on mobilizing the knowledge itself? Thank you.
Good morning. My name is Ken Rubin. I'm the community coordinator for BPM Plus Health, and I'm here to talk a little bit about the business case and the importance of care processes as computable artifacts. So we'll start with really a look at the landscape, and much of the attention in industry today has been focused on data and data interoperability. And the upshot is that data is the record of what's happened before now, but everything that affects care and care delivery is process and knowledge integrating with that data to provide care, and that's what happens from now, and that's really the part we're here to talk about today. Effective health IT integrates data, knowledge, and process. So it needs to bring all these together so that at a point in care, a caregiver, a provider can make an appropriate informed decision. Context is particularly relevant because the body of knowledge of medicine is growing exponentially. So our ability to consume that knowledge appropriately and effectively for a given patient in their situation is a big challenge. Providers often don't have visibility across the entire continuum, and that presents a challenge. So the issue is, how do we more effectively bring knowledge and process to that point of care in a way that we can consume that effectively and keep pace with this ever-changing landscape? This visual, I think, illustrates this well. So we have data kind of at the core, and there are a series of standards that have been evolving that kind of build on that. FHIR, CDS Hook, CQL, and ultimately BPM is about this evolution from data sharing toward intelligent automation. Without changes, keeping pace is untenable. I mentioned that clinical practices are evolving. It's 17 years from the point of a new medical discovery to the availability of that at the bedside. And the body of knowledge of medicine is doubling every 6 months. So effectively, if we were to have 1,000 data points of medical knowledge today, that would evolve to 9 trillion in 17 years. So the way we currently do things just isn't sustainable. So this is really making the case for why we need, BPM plus health. Status quo is no longer an option. And BPM is about taking these care processes and expressing them using computable formalisms. We've developed a field guide for shareable clinical pathways, which allows you to not only document these models, but then serialize them and execute them in software. This approach, it's a community of practice, it's standards oriented and ultimately supported by COTS tooling. Thank you very much.
Okay, so thank you very much, all of our lightning talk speakers.